Welcome to the ftir.fun Infrared Learning Series. This episode, Ep20 Introduction to Quantitative Analysis, Lambert-Beer Law. Then close with a checklist. Next, IU, from what to how much. In 1760, German mathematician Johann Heinrich Lambert wrote a seemingly simple proposition in an optical treatise. The intensity attenuation of light passing through a medium is exponentially related to the medium thickness. In 1852, German physicist August Beer extended this law to solutions. Attenuation is also proportional to concentration. This became known as the Lambert-Beer law. Next, Lambert-Beer law. 1.1 Derivation of the law. Consider a monochromatic light beam of intensity $is $0 passing through a solution of thickness $B and concentration $C, resulting in intensity $I. Next, peak height vs peak area methods. Method excitation. Measure the perpendicular distance from the peak top to the baseline. Figure 1. Geometry of peak height method. Next, IN. Calibration curve method. The calibration curve method, standard curve method. Calibration curve method is the most commonly used method for quantitative analysis. 3.1 Establishing a calibration curve. Next, IV. Pay-per-pallet quantification. Pay-per-pallet method is the most commonly used for solid quantification but has special considerations. 4.1 Path length issue in Cabral pellets. Next, V. Liquid cell quantification. Liquid cell quantification is the gold standard for liquid samples with precisely controllable path length. 5.1 Measurement of liquid cell path length. Next, attribute quantification. Although atrial path length varies with wavelength, quantification is still possible under fixed conditions. 6.1 Feasibility of attribute quantification. Next, multi-component quantification. 7.12 Component quantification. Principal excitation. Both components absorb at two characteristic peaks, but with different ratios. Next, precautions in quantitative analysis. 8.1 Path length consistency. Transmission cells X use the same cell for all samples measured. Actual path length in Tiern's fringe method. Keep cell windows clean. Next, I-pull. Determination of a component in a mixture. Let us demonstrate the infrared quantitative analysis procedure with a complete example. Objective. Determine acetone content in industrial ketone-ethanol mixture, known to be about 20–50%. Next, or quantification via SUV chromatography. 10.1 Advantages of ear quantification. No separation required. Directly measure mixtures. Instructive, suitable for process analysis. Next, best practices for quantitative analysis. 11.1 Method development goal. Validation, accuracy, precision, load. Low sample measurement replicates greater than or equal to 3 reporting. Include complete method description. Next, a rule for thought. Under which conditions does the Beer-Lambert law $A equals Beer dam EC $fail? List at least 3 common causes and explain how to detect and avoid them. You need to determine the content, about 50%, of an active pharmaceutical ingredient in a Cabral pellet. Design a complete quantitation scheme, including internal standard selection, standard preparation, calibration curve construction, unknown sample measurement, and expected precision. Finally, the drill actualists. Make sure you can recall each item. Lambert law. A equals where against dot BC $. Applicable conditions. Monochromatic light. Dilute solution. No scattering. Homogeneous fixed path length. Molar absorptivity. Infrared where A bond is 10,000 times smaller than UVVs. Optimal A range. 0.3至 1.0. Peak height method. Simple and stable. Affected by peak width. Peak area method. Less affected by peak width or suitable for broad ear peaks. Calibration curve method. Pervasive M standards. R-carat to $0.999. Detection limit. Log. $3 sigma K $. Quantitation limit. Log. $10 sigma K $. K per pellet quantitation. Internal standard. KSCN at 2050 centimeters. Liquid cell path length measurement. Interior's fringe method. Quantitation. Fixed conditions. RSD 15%. Multi-component quantitation. Solving simultaneous equations. PLS. Transmission liquid cell precision. RSD 0.51%. Kipro palette precision with internal standard. RSD 3%. AS precision. RSD 15%. Pharmacopoeia requirements. D%. Spike recovery 98, 102%. Comparison with UVV. Lower sensitivity but higher selectivity and information. Comparison with chromatography. Lower sensitivity but faster and non-destructive. Suitable scenarios. Concentration 0.1%. Process control. In situ monitoring. That covers the required sample for this episode. Practice with real spectra on ftir.fun and continue with the next lesson.